So,
Another question.
an online participant.
Yes, yes. We have online participant also?
Yes,
Yes.
online participant.
O şimdi Paris'te zaten olmaz.
No, from ABA University. Okay.
Yes,
Our
sir.
today's topic is construction of tangent of conchoid of Nicolet-Descent, limitation of Pascal, and solution of extremal chord problem in ellipse using chronodal cystoid curve. Very lazy name, but I will explain.
Yes.
Just a short announcement before we start. I applied for vaccine website mathnet.ru to put our seminar there, all the details, abstracts, information to that portal. They agreed, they already put it in their website of mathnet.ru, but there was one condition that we should have a logo.
Okay. Logo.
I chose this.
But it should be our design.
It is this shape. You can look at it.
Okay.
It is a mathematical object. Yeah? It is called loxodrome. When ships pass horizontals with the same angle, they make infinitely many loops. Infinitely many loops around the poles before reaching it, actually never reaching it. Okay, so it is an object, mathematical object. I thought it can be our logo.
Agree. Never mind, no problem. Yes, that image take off.
What? Must, okay.
Everyone is that image from internet. Then we have to take permission, or we have to design.
It is the image of this. It is the photo.
You take a picture of yourself.
Yes, it is the photo.
Finish.
Okay.
Logo accepted.
Okay.
Yeah.
So let me.
Something.
Okay. Let me start.
Yes.
With something very old, Apollonius problem. This slide just intends to show that this kind of problems were discussed long time ago, even during the time of Greeks. So, for example, Apollonius asked this question. Imagine you have an ellipse, and you have a point. Where should you choose P so that OP is maximum or minimum? Okay, it is equivalent to find normal, because if it is minimal, it should be 90 degrees. There is no other option. And Apollonius solved this problem. It is a hard problem in his book, very nice book. No, it was after Jesus Christ, but it is still very old problem, old book. Okay, I just wanted to say that this kind of problems are indeed very old.
What's the date? 262 BC.
260 something.
BC, huh? BC.
Before.
After.
But then BC, I don't know.
Are you sure?
Before Christ.
Maybe I made a mistake. Yes.
It should be after, right?
It should be after.
Okay.
Maybe this is right.
From 21st century, it's not math actually.
Yeah, for us it doesn't matter.
Okay. This lemma will be crucial for the rest of the talk, so I will try to motivate this with some examples. So in calculus, what do we teach to our students? We say when the function is maximal, when the tangent line is horizontal. Yes. It is equivalent to say that derivative at c is equal to 0. From geometrical point of view, it means that this is horizontal.
Or there is no derivative.
Okay. For Greeks, it is horizontal. Okay. For ancient Greeks. For us, it is derivative is equal to 0. What if there are two curves? When do we say this distance is maximal or minimal? When does this happen? This is F, this is G.
Difference of derivatives
Yes,
is zero. For undefined.
fx minus gx prime should be 0. Or another one,
What is the geometry meaning of this?
f prime c is equal to g prime. What is the meaning of this?
Parallel tangents.
Şey değil mi? Average.
It means, for example,
Average değil.
it happens, for example, here. This tangent line is parallel to this tangent line.
Generalization of
Now imagine we do this same, but with polar coordinates. You have a pole, and this function, rho equals rho theta. And now we ask when r theta is maximal. Actually, this one is the same. F prime theta should be 0. What is the geometric meaning of this? For example, here imagine it is maximal.
Yes.
Tangent line should be perpendicular to the radius. Now, let us ask this kind of question for polar coordinates. Imagine we have two curves, and we want to make this maximum. Okay, this is R1 theta, this is R2 theta. When this is maximum.
We need to construct new curve.
What is the geometric meaning of this? Of course, it is R2 theta minus R1 theta
Sum of tangent
equals 0.
şeyler ne güzel. Sum tangent of angles must be equal 0.
Surprisingly, this was not much discussed in the literature. I didn't find a literature in which someone wanted to find a geometric meaning. Here is the geometric meaning. For example, you can look at this case, one curve, another curve. If AB is maximal or minimal, extremal, largest or shortest, then you should draw the tangent curve lines of these curves at those points. They intersect somewhere. And from that intersection point, you draw perpendicular back to this line. OA should be equal to BD. Very surprising geometric interpretation. Not so simple, not as simple as this. I'll just take a picture. Okay, so this is the geometric meaning. This is the geometric meaning of this AB being maximal or minimal. The same is true when the curves are on the different sides of point A. The same algorithm. You draw tangent from A, tangent from B. You draw perpendicular from their intersection to AB.
OA equal BD.
OA should be equal to BD. So this is the geometric meaning. This lemma will be very useful for many problems that we are going to discuss.
This was a lemma, right?
Yes, it is lemma. We will use it a lot.
So your
What is it
I
actually
hope that my
in terms of, if we back to this picture or in terms of what is this part and that part, they are tangents or okay.
tangent lines intersect. I can explain here too. So you draw their tangent lines. Okay. Imagine these tangent lines intersect somewhere. You draw perpendicular from there. This should be equal to this. Okay. This is the geometric meaning.
So if they're equal, you mean, what about it?
Middle, it is not important. If it is maximal or minimal, this should be equal to this. This is the lemma. Okay. Okay. Now I will use it in some simple problems, and then we have harder problem. Okay. So first of all, this definition, conchoid of Nicomedes, another Greek mathematician. The Greek or ancient mathematicians liked curves a lot because there were problems which could be solved only by curves. No compass straight edge constructions were possible for them. For example, trisection angle or doubling cube. There were some problems which could be solved only by some curves. Nicomedes discovered this curve when he wanted to solve one of these old problems. So what this curve does, how do we construct this? Imagine we have a point A, fixed point, and this distance BC1 is given, fixed. Okay, it is given, it is equal to A, small a. And you rotate this line around point A, always keeping BC1 the same. Okay, the locus of point C1 will be Nicomedes conchoid. Okay, it is the name of this curve. That's how you construct it.
BC we choose fixed.
Fixed. B moves, this line rotates around A. A is
So
always
is fixed.
B is
C1
not
is
fixed.
moved.
A is fixed.
A is fixed. BC length of BC is.
Length of BC1 is constant. As you rotate this line, C1 moves to keep the distance constant, and it draws this curve. It is called Nicomedes conchoid.
Sorry, how you we take, so we choose
A.
we choose BC.
We choose
So
a fixed,
BC1 will be fixed.
we choose fixed line.
Oh, yes. We choose
Line is
fixed
also
line.
fixed, and BC1 is constant. And when you rotate this line,
From rotate from A.
A is
So
fixed.
BC1 will change that.
BC1, B changes, but you keep C1 at such a distance.
B change along the horizontal
It means
line.
that AB will increase.
AB will increase.
Yes.
Okay.
But
B
B-
on line.
C is going like, okay.
Yes.
BC1 is kept constant.
The upper curve is the generated curve, not the given.
No, it is not
Okay.
given. There is also a counterpart of this curve
Yeah.
below.
Length of AB will change.
Will change.
Yes, but
BC1 will just,
Yeah.
If you will also take BC2 equal to that same constant, there will be another branch of this curve below the line. Okay, this is called conchoid of Nicomedes. Nicomedes used it to solve his trisectional angle problems. There were no coordinate system at that time, no Cartesian coordinates, no integrals. Okay, so how can we apply our lemma to this problem? So note that BC1 is constant. It means that if BC1 is constant, then it is always maximal and it is always minimal. So this property should hold everywhere. So this should be equal to this everywhere. This gives us an idea to find tangent of Nicomedes conchoid. Tangent. Straight edge construction of the tangent of Nicomedes conchoid. Little bit complicated picture, but I can explain. First, you find a point D1 such that C1 D1 equals AB. AB is already in the picture. Curve is already there. Conchoid is already there. So you can measure AB, and in the extension of BC1, you can take point D1 such that C1 D1 equals AB. It is possible to find such a point. You can do the same on the opposite side. You can find C2 D2. C2 is given, it is on the conchoid. You choose a point D2 such that C2 D2 equals AB. So you find these 2 points. Then at these points, D2 and D1, you draw these perpendiculars to the line, and those perpendiculars intersect the original given line at E1 and E2. And then you connect C2 with E2 and C1 with E1. You will automatically obtain the tangent line of this conchoid. Why this lemma? So we use the lemma in the opposite way, from back to front. Okay. So I didn't see this way of constructing tangent of Nicomedes conchoid in the literature. Because the lemma gave this to us for free. Another, okay, there we can also solve some interesting examples. For example, we can show that if you draw perpendicular from F, there will be a point G, and surprisingly, the locus of point G is a line, so it is always at the same distance from this line. Another interesting property of Nicomedes conchoid, which we obtained for free. Okay, without much efforts, we found an interesting property of conchoid. Okay. This is an elementary example that I used for it. Another similar curve. Imagine doing this not with a line, but with a circle. Okay, I will explain this. It is called limation of Pascal. Limation in French means snail. This Pascal is not like Pascal. It is not Blaise Pascal. It is Étienne Pascal, the father of Pascal's the father. He was also a mathematician.
So the family, Pascal family.
Pascal family. So Pascal does the following. Imagine you have a point on a circle, point A, and a fixed distance. Okay? Fixed distance A. It is given. You draw an arbitrary line which passes through a point B, and on that line you take point C1 such that this is equal to A, that constant.
And the same with the start.
Okay, same idea. Yes. You do this for all such lines, It will be a curve like this. Okay, it is called
You take chord and then continue chord with interval A.
Yes, constant.
Starting from point A.
Yes, it will
create chord. Okay.
Okay.
Chord A. And then add to this chord AB.
Yes.
Interval A. Okay.
If you take in the special case, I'm not sure in what special case. In a special case, you obtain cardioid, heart-shaped curve. This happens when A is equal to, I think, diameter of this, if I'm not wrong.
So when A is on the circle, it's cardioid, otherwise it's limation Pascal.
So if A is larger than diameter, you will obtain a curve like this. But if A is smaller than diameter, you will obtain a curve which has a loop. It intersects itself. But if A is equal to exactly the diameter of the circle, then you will obtain this cardioid, another interesting curve. Note that there are again two such points. One is on this side, the other one is on this side.
So just but assume that we take point here. Okay, nearest.
Okay.
And then the same A here.
Okay. And also there is another pair, which is here.
Cardioid when it's equal to diameter.
No, I mean, this is a chosen interval fixed. You choose that one, yes. And we have to take this, no?
Yes, we connect all of them and we obtain a shape like this.
Okay, good.
It changes depending on age. Its shape can be sometimes like this, sometimes like this. It can even have a loop. Okay.
For which interval A, what is the relationship between radius of circle and length of interval A? So to see different pictures.
Okay, this here radius is smaller than A. Diameter is smaller than this A. Here, diameter is exactly equal. If diameter is larger than A, then there will be a loop here. Okay,
Maybe
maybe
A is I think larger.
maybe
than
there
diameter.
will be such a picture in the future.
I think A is larger than diameter.
Okay.
Yes, here A is greater than diameter.
Okay.
Okay. Again, when BC1 is maximal,
Again, what?
BC1, when is BC1 maximal?
Diameter, I mean,
No, for fixed A is fixed. It is not, it is always the same. It is always constant. So according to lemma, the property,
What's the question again?
when BC1 is maximal, it is constant. So it is always maximal. Yes.
What's the goal? I mean, what's our goal?
We want to apply our lemma. Do you remember the lemma? We want to apply this lemma there. Okay. Imagine that this is maximal. If this is maximal, then A should be equal to BD. And now we have two curves, a circle and a lemmaton of Pascal. Okay. When is this maximal? We ask the same question. But for this construction,
It's the same.
it is constant. So that property should hold always. For any point B, this should hold. So how the picture will look like in this case? You draw the tangent of circle, yes, and tangent of lemmaton. They intersect at E1, drop perpendicular to the original line AB. Then this C1 D1 should be equal to AB. But that will give us a recipe to find tangent of the Pascal's lemmaton. How? Imagine this tangent was not here. I have AB. I have also C1 because this lemmaton is already here. I will extend it to C1 D1 to this length. And from here, I will draw the perpendicular.
Find out.
And also the tangent line of this circle. This will give me the point E1. And when I will join E1 with C1, I will get that tangent line. Okay? So it gives us a recipe. Another interesting application of this lemma. So there are again some other nice questions that we can ask here. For example, again, you can also draw the tangent line at C2. These two tangent lines intersect at F, and from F you draw perpendicular. You obtain this new point. The locus of this point is a circle. So I obtained a new property of this lemmaton of Pascal for free. $0. Okay.
you have spent a lot of time on it.
Actually, that didn't take much time because it is just a consequence of that. One more interesting property, but this is only for cardioid, that's special case. For cardioid, the angle here at F, C2, F, C1, this angle is 90 degrees. I didn't know this was true. After this, I proved it. Also, E1, F, E2, this angle is always 90 degrees. Another interesting property is that locus of point F, as this moves, is a circle. I didn't know this was true. Again, it is a direct consequence of this lemma. Okay, enough this motivation. Let us go back to our problems. So, in geometry, there are many extremal problems. Some call it geometric inequalities, others call it geometric optimization. Okay, there are many problems like this in geometry. It is a whole branch.
New branch? No.
What?
Is it a new branch?
No, it is not a new branch, but
But the set recent development.
yes, there are many nice books about this, many new papers. Geometric optimization. Okay. One typical question. Imagine there is an angle and a point inside of this angle. how should I draw this line passing through this point so that the area cut by this line is given? Interesting question. Yes?
Just a minute, I don't understand. So how should you choose a point?
No, point is chosen. Point is chosen. Angle is chosen.
Okay.
That's why I put exclamation mark. This line is unknown.
Uh-huh.
Where should how should I draw it so that the area cut by this angle, cut by this line, is minimal? Surprisingly, the answer is when this is equal to this. Okay, when that line is cut so that this point divides it into two equal parts. There are other nice things like this. I want to show you more like this, more problems like this. Imagine again, point is given. You want to draw such a line through this point. This angle is given, point is given, such that the perimeter of this triangle is minimal. Another such optimization problem. The answer is again unexpected. Let us first.
Now it's expecting me. You're seeing the area problem, maybe we can expect it.
But the answer is really unexpected. Let me show you. To make that perimeter minimal, you should first draw a circle which passes through this point and touches the sides of the angle.
Then tangent, huh?
And then tangent line to this circle will give you the triangle with minimal perimeter. Any other triangle, any other line will cut a triangle with larger perimeter. Okay? This list can be continued. There are many such problems in geometric inequalities, geometric optimization.
Sorry, again, you take a
Angle and the point.
yes, I mean circle. Circle. Yes, yes. You create a circle through the given point
And touching.
with touch. Yes, with tangent. Almost one day.
It is a construction problem.
Yes, yes. No,
Okay.
so, and then what is this line? Last line.
Last line should be tangent to that circle.
That circle at this one.
Yes. Okay. There are many problems like this in geometric optimization. Surprisingly, the simplest question is the hardest one. Such as usual. So imagine again, we have a point inside of the angle. Okay. Again, angle is given, point is given. Exclamation mark means that they are fixed. Now, question is to draw such a line that this distance is minimal. Okay? When is this minimal? How should you draw it? Draw it like this, draw it like this. Which line will cut smallest segment? Okay?
Let's think about spatial case. Actually, if the sides are equal,
Can we apply something?
Which these two are equal to each other.
if they're
That's not the
answer.
but
It's not given.
there is no side here. It is infinite ray.
Understand. I'm sorry. I want to say that if you have right angle triangle.
Right, 90 degrees here.
No. Even no.
Here,
It's 90.
maybe for 90 degrees it will be a little bit simpler. I agree. For 90 degrees it can be a little bit simpler. But for general angles, it is something difficult.
For energy.
Actually, we have already answered the question. Imagine this is one of the curves, C1. This is the other curve, C2. The tangent of these two curves are the lines. The tangent is the same curve,
Yes.
isn't it? So, according to lemma, their intersections is this, and if you draw perpendicular back to this line, if this is maximal, then this should be equal to this. This is so it gives us a condition to find such extremal line segments. Okay, If it is
This one is maximum.
if it is minimal, actually there is no maximum because you can make it arbitrarily large. There is no maximum, but there is a minimum.
Minimum, yeah.
If it is minimum,
Extreme,
then
yeah.
it should be equal to this. This is the classical fact. Many people knew this before. This is in classical geometry books. So it is a known fact. You can,
to solve this exactly.
you can prove it using calculator, or you can use polar coordinates for this. Okay, so if you want this to be minimal passing through D, you should make sure that AH cuts in so way that BH is equal to DC. This is the condition that makes this line minimal. Any other line passing through D will have larger length. Okay, this is classical result. So in this problem, there are two lines. Have you noticed it? First line, second line, and there is 1 point. Two lines, 1 point. I thought maybe I can find a problem in which the rows of lines and points are changing. Okay, something like this. So imagine we have 1 line, but 2 points.
1 line by 2 points. Yeah.
Here we wanted to find what? Line, yes. Now I want to find point such that the sum of these two is minimum. So similar problem, but rows of lines and points are changing. Okay? So this point is given, this point is given, this point is changing, this line is fixed. We want to make the sum of these sides.
Yeah, you produce new problems. Yes.
The sum of these two lines is minimum. I worked a little bit on this problem. I found some interesting results. So for example, if you restrict only 2 points which are on this parallel line to the original line, then there is a nice solution to it. For this sum to be minimal, you should take this point in such a way that this is perpendicular, this is also perpendicular, we draw this perpendiculars. And then this perpendicular should be equal to this perpendicular. If this happens, then this sum is minimal. If these two are equal to each other, if you go a little bit to the right, this will change. It will not be any more equal. Okay, not like this. So there is a one place which gives you minimum. Okay, and at that point, this equals to this. I proved it. I can also express it as an inequality. It is here. But for the general problem, I couldn't solve it. So not restrict on one line, arbitrary point, okay, not on one line, arbitrary point. Where should I take this point to make this sum minimum? I have a conjecture for this. I expressed it like this. So it should be in such a, the point should be in such a way that when you draw tangent line, no, angle bisector, and then from the end point of angle bisector, draw perpendiculars to the sides, then this should be equal to this, and this should be equal to this. But I couldn't prove it, okay? This is just conjecture. If you are interested, we can work on this problem together. So for any other point, C1, the sum of CD and CE will be larger. Smallest one corresponds to the case when CA equals DL and CB equals ME. The smallest one is given by this.
Yeah, it's the only condition.
Okay, it is the last problem that we are going to discuss using this lemma. Imagine you have an ellipse. It can be replaced also with parabola or hyperbola. Imagine you have an ellipse and a fixed point in it, fixed. How should you draw this line? How should we draw this line so that the length of chord AB is minimal or maximum? X is fixed. How should I draw it so that the length of this chord passing through X is maximal, or
X is arbitrary choosing point.
yes, fixed, ellipse is fixed. How should I draw this line so that it is part inside of the ellipse is minima?
Okay.
Logical question. Surprisingly, this question didn't attract much attention in the literature because it is relevant problem. There is no formula way to solve it, okay? No concrete formula.
Because it depends on the average X paper.
It depends on X, it depends on ellipse, and there is no, how to say, explicit solution for it. Okay, we can solve it only geometrically, like these problems. I want to show you how I solved this problem.
You mean solving constructive?
Constructive, what do you mean by construction? Do you mean constructible with compass and ruler, or other instruments are allowed? I can solve it with some curves, okay?
Yes, it will be when we move the line, this line, we'll describe what some curve, I mean, a new curve, if you choose number, yeah, let's see.
Okay, so I'll solve this using, again, our lemma. For this, I need two curves. C is the given point, this chord. I choose point E such that this is equal to this. Okay? It is easy to prove that the locus of point E is another ellipse. Okay, I can even write it as equation. C is fixed. As I move AB around C, I can choose each time a new point E such that AC equals EB.
So first, external ellipse is given ellipse.
Yes.
You choose arbitrary C.
Arbitrary C is given.
C is given point in external ellipse.
Yes, in external ellipse.
But how do you take E?
So each time I draw this chord,
Okay.
I can measure AC.
Yeah, and then yes, find out.
EB, I can find EB such that this is equal to this.
Is it possible?
It is always possible. If there is a line, and this is given. You just choose a point so that this is equal to this.
So I mean,
This E will be on this ellipse.
ellipse, I mean,
No.
external part will be ellipse?
The external is a given ellipse.
Yeah,
This
yeah, I understand, but
locus
the
of
point will be,
an ellipse. This will be an ellipse, a smaller ellipse. I can even write it as equation. Let me explain you. This is ellipse, this is point.
Yes.
Each time I draw it, I find a point such that this is equal to this. Each time I draw it, I find a point such that this is equal to this. Each time I draw it, I find a point such that this is equal to this.
So T is increasing or decreasing part to
Okay,
A.
So when I will join all these points, I will get an ellipse. Okay, I can even find the formula for it.
okay. Good.
This is one of the curves that I need. Now the other curve. I draw tangent line to original ellipse at A and at B. Okay, these tangent lines intersect at D, and from D I draw perpendicular. And the end point of this perpendicular, E, has a locus. Its locus is this strange curve. Its name is also strange, cronodal cissoid. Okay, cronodal cissoid. It is
Is your name, yes?
no, it is a name known in the literature. Cronodal means that it has a node. There are also cissoids without any nodes. Okay, since it has a node, always has a node, we call it cronodal cissoid. Now, if we intersect this inner ellipsoid with this cronodal cissoid, their intersection will give us exactly the points at which maximum and minimum will occur. Let me show you. So if that ellipse and inner ellipse and that cissoid intersect at E1 or at E2, okay, one of them will give us the maximum, the other one will give us minimum. Why? Because of that lemma. Do you remember? Tangent lines intersect at a point from which you can draw perpendicular, and then when you draw perpendicular, this should be equal to this. For this ellipse, this is equal to this. For the other one, you have this construction. So when they intersect, you have both of them. This is equal to this, and the tangent lines have a perpendicular from this. So both of them hold true. I found equation of this. I shouldn't write all this. Probably. Okay, I found I found an equation of it, which we can, using some affine transformation, reduce to this, and it is known that this is indeed the equation of coronodal cissoid. So it is known in literature as the equation of coronodal ellipsoid or cissoid. So this solves our problem about extremal chord of ellipsoid. From this paper was published in Turkish Journal of Nature and Science. They liked this problem, this paper so much that they took pictures from this paper and put on the cover page of the journal. There were 10 something papers. They liked it. The pictures are put in the front page.
Which year?
In which year? It was in 2000 something, 2013. Long time ago. And here are my references. There is
No reference to
Azerbaijani reference here. Maybe you have seen this book, Garibe Eğriler, Nasibov. This is a very nice book, inspiring book in Azerbaijani language.
Professor Vladimir Pavlovich, Professor.
Yes.
Şaşırdı o şey.
Yunanistan'da referans var. Yunan, yani birçok Christmas Yunanları.
I think I didn't mention them, but there are books which mentions them. For example, this old book from 1900. Okay. Thank you. That's all that I want to
Thank you very much. So just one question.
Okay.
So there are lots of problem of Charin's program.
Okay.
Geometry, also optimization problems. Yes.
Yes.
Charin's problems. Just I saw many problems in many problems which were motivated by Charin's problems in geometry, optimization problems in geometry, among the Kazakhstani mathematicians. I mean, which are interested in application to plane geometry.
There are many problems, including Sharingan's problems. His book about geometry problems is a very inspiring book.
I think that the Charin's problem, there's a 2 volumes or 1 volume book, Charin's problem.
The second volume is about space geometry, so it is not that.
The author is Charin's problem, author of the, not Charin itself, but himself, but Charin's problem books.
Okay.
Yes, there's a Charin.
I didn't.
So around the author is one of a Russian mathematician.
Maybe.
Yes, I had such a book. As a yes, they give me this book as a present, but I don't know.
So, you know, it is a tradition to give gift given to you to another one. So you can give it to me. I will accept it.
Yok, herkese muhalefet saklayayım onları bir de. Şahin değil de Şahin'den, Şahin problemleri hakkında.
Okay, Farid, do you have any questions? No questions? Okay, then I stop this session.
Maybe it's Farid.
Maybe yes, please.
Yes, Farid Farid. Okay, bye. I will stop this recording.
Thank you very much.
Thank you for coming, Farid.
Thanks, many thanks.
At the end, stop.
Okay,
Yes.
stop recording.
We are